Okay, our next speaker is also a Tom. Tom Talpey from Microsoft. We figured since the two talks, since the two operating systems are so close to one, we would have the same name for presenters. I'd actually like to thank Tom Talpey a lot. So Tom is one of the rock stars on the whole persistent memory. He does a lot of work in here. My heartfelt appreciation for that. Tom let us know about 2 weeks ago that there's a good chance he would not be able to be here. He had a family conflict or something, and he was being a good citizen and letting us know. And but he was able to evidently reprioritize things and get things straightened out, so he was able to be here. So, a testament to his dedication. So, thank you, Tom. I don't want to get too teary-eyed here, you know. So
please don't.
So anyway, Tom Talpey, as I said, Microsoft. Like I said, one of the rock stars. Tom, take it away.
Okay. Thank you, Jim. Yeah, it was a little dicey, but I managed to push one thing earlier and one thing later and opened up the week. So here I am, and I'm glad to be here. I'm Tom Talpey. I'm an architect in the storage team with Microsoft. We've been doing the NVDIM thing for a while, both at Microsoft and me personally. You may see me mostly talking about remote access, networked access to this type of thing. I work in the SMB3 technology. I work a lot in RDMA technology, in particular putting SMB3 on top of RDMA with some very spectacular results over the years. And NVDIM is, a new paradigm in storage, low latency, ultra low latency. Latency is really what distinguishes it for us. So I'm going to pivot a little bit. I'm not going to talk much about SMB. I do have a slide at the very end. But I'm just going to talk about the support for NVDIM itself as a storage medium in Microsoft Windows. Okay. So I'm echoing the talks that were given by my colleagues Neil Christensen, who's an architect in the storage, the NTFS, the local storage team, as well as Tobias Klima, and the SQL team, Lindsay Zhu. They've given some presentations at both the Intel Developers Forum and at Microsoft Ignite. And Neil represents NTFS and DAX. Toby and Lindsay represent SQL Server. So I'm just going to bring these in as features in Windows which enable NVDIM, persistent memory in general, and SQL Server for a bit of a performance story. Not a very big one, but just to convince you that this is real and available today. So I'm just going to talk a little bit about Windows persistent memory support, what's there. Windows persistent memory storage access details. It'll echo Tom Coughlin's presentation in some ways, I think you'll see. And then follow it up with the SQL Server 2016. So, position statement. Persistent memory is supported in Windows 10 and Windows Server 2016. And we mean that. These are delivered products, and they are there. Persistent memory support is foundational in Windows. We consider it a foundation technology, something which we can expect of platforms on which Windows runs, right? And it's SKU independent. It runs on client SKUs, the so-called workstation or Windows 10 SKU, as well as the server SKUs. It supports JEDEC-defined NVDIMN devices today, available starting from Windows Server 2016 and the Windows 10 anniversary update. That was the version of Windows 10 that we shipped back in the fall. I think it was September, October. That's different from the Creators Update, which is the next one coming out. There will be unspecified new features then. We support several different access methods to persistent memory. And there's a very good reason for this. I'll tell you in a minute a little more detail about it. But I'll just list them for the moment. The first and probably most ubiquitous one is the direct access DAX file system. And you notice that DAX is the name used by Linux. That's not an accident. We originally called this DAS, D-A-S, and we found everybody was getting confused. And we said, well, it's the same goal. And so we changed the name. So we're all going by the same handle these days, okay? Direct access DAX, you'll see it very familiar. Totally different thing in Windows, right? But the same basic principle and the same basic goal. Mapped files with a load, store, flush paradigm, as well as supporting cached and non-cached with the files with a read-write paradigm. Okay, and this is for application transparency as well as performance. Second, we support a block mode, the so-called persistent RAM disk, or I just basically made that a handle here. But the idea is that it's a raw disk paradigm, right? There's a block device which emulates a disk on memory. It just happens to be persistent. That's why it's different from an old-fashioned RAM disk. And application interfaces are the third major way to do this. The mapped and traditional file, which we inherit from DAX for the most part. The NVM programming library, which Andy mentioned earlier and which Tom just mentioned a minute ago. This is the open source library. It's supported on Windows, and it will be there in the future, not too distant future. And finally, PMEM-aware applications, which are just open-coded, right? If they have access to a chunk of memory that they happen to know is PMEM, they can do their own flushes, they can write their own code, have a ball, non-temporal, whatever, part of it. Windows goals for persistent memory to support zero copy access to persistent memory, full performance, minimum latency. All right, it's the real thing. Okay, nothing in between. Most existing user mode applications will run, this is a goal, without modification, right? So there will be ways for an existing application to use PMEM without modification. That is incredibly, incredibly important. I've worked on a lot of new systems that required application changes. A lot of t-shirts when those things didn't come true. Because applications don't change. They change very, very, very slowly. It's really important to have that on-ramp, that low barrier of adoption of your new technology. This is a huge goal here. So we have an option to support 100% backward compatibility into the future. There may be new types of failure modes, right? Things don't behave quite the same way on a RAM disk versus, or a persistent memory RAM disk versus a real disk. But we want to provide 100% backward compatibility as much as possible. And a sector granular failure mode for application compatibility. And this is similar to what Tom was describing before with that BTT and things like that, right? No torn pages. Sector granular. So, what do we provide? A new driver model optimized for persistent memory hardware. There's an SCM bus driver. It's called SCM bus.sys. It enumerates, finds, if you will, the physical and logical persistent memory devices on the system. It's not part of the I/O path. It's just there to kind of plumb the stack and find the devices and plumb the stack. What kicks in is SCM disk drivers, which are the drivers for the actual logical PM devices that the SCM bus driver found and enumerated. It's a storage abstraction layer to the rest of the OS. It's hardware specific, right? There'll be different types of hardware down there. But they will all be provided by the appropriate generic or device or manufacturer-dependent device drivers. Windows will use a native 4K sector size. 4K, no more. It introduces some new interfaces. There's a byte addressable storage functionality and management of PM hardware. Those are part of it. So a new class of volume is this new direct access storage, otherwise known as DAX, volume. Memory mapped files will provide applications with direct access to PM, right? That's the maximum performance one. You'll open a file, you'll map it into your address space, you can load and store to it with single instructions. Totally in user space, load, store, nothing but you and the hardware. To create a DAX volume, it's chosen at volume format time. I'll give you a couple of real-world examples. Why? Why didn't we just, why do you have to choose? Compatibility issues with various components. The big examples are all those other things that use file systems or that go along with file systems. Filter drivers, there's a bazillion of them in Windows. BitLocker, volume level software encryption. And most deviously, VolSnap, the volume snapshot provider. These layers need to know what underlies it, and they need to be configured in. Some existing functionality is lost with DEX. There are certain types of filter drivers that don't work. There are, if you read, I'll give you a reference to Neil Christensen's presentation. He'll give you much more detail on this. There are a large number of filter driver-like operations which work completely transparently, but some others which may not work quite so transparently. DEX volumes are currently supported by NTFS. So in effect, what you've done, what you're doing is you're formatting an NTFS volume on this persistent memory device with a special flag for DEX. I'll show you what that flag is in a minute. And they ship as part of Windows 10 and Server 2016. So they're all working as we speak. On DAX formatted volumes, memory map sections map directly to the PM hardware. So it's a one-to-one mapping, right? No translation, nothing in the middle. When an application creates a section, memory manager asks the file system if the section is in DAX mode, and the file system returns yes. Magic things happen when that path is available. This is the zero copy access to storage. This is what we expect will be the maximum performance and the one that most applications will want to use. It's a memory map paradigm, right? So a memory mapped an application that already worked on memory mapped files will do this easily. Maybe the error semantics will be a little different. Maybe some other things will come into play, but it'll work quickly. It might be a bit of a stretch for a read-write application to use it, okay? And that's what we're going to talk about in a minute. No paging reads or paging writes will be generated. That's a big difference from traditional Windows file systems. There's a lot more detail about this in Neil's presentation. I didn't want to get down to that level too much, but I'm just going to leave in that red letter. Cached I/O index mode. So let's say we don't have a memory mapped aware application. We have an application that opened files and did a read and a write. Read and write in Windows is supported either via cache or non-cache data paths. Cached I/O is a pretty efficient model, as you'll see. The cache manager, that's the guy who handles the cache, right, above the memory manager, creates a cache map that maps directly to the persistent memory hardware. So when you open a file in cache mode, the cache is the page in the file, right? Normally the page in the file is sitting on a disk and it's been loaded into memory. Here, we have one copy of the thing. It's both memory and the backing volume, okay? So that takes a copy or an I/O or whatever out of that operation. Once it's in cache, it's in the device. The cache manager copies directly between the user's buffer and persistent memory. So if he does a read or a write, it pulls the data out of the user's page and puts it in the cache page, which puts it in the file. So it's one copy access to storage. One copy, minimum number of copies from the user's data to the file data. Cached I/O is therefore, and importantly, coherent with memory mapped I/O. So as the same I/O is hitting the same device, right? There's no bounce buffer in the middle. So once it's in the cache, it's there and it can be seen by somebody who memory mapped the same file. As in memory mapped I/O, no paging reads or paging writes are generated. So there's no cache manager, lazy writer thread, blah, blah, blah. This is all just flowing straight down to the hardware. Non-cached I/O in DAX mode. Well, what do we do if it's not buffered? Well, guess what? We buffer it. We basically set the flag and buffer it. And you ask for non-buffered I/O. Well, oops, I'm sorry, I buffered it because I'm actually more efficient in buffered mode than I am in unbuffered mode. In unbuffered mode, I'd have to put it in another buffer before I put it in the file. That would be slower. That's not what you want with non-buffered mode. So this is really interesting, and this becomes really important when we go remote. I have a whole presentation about this at last year's Storage Developers Conference. All right, but it's also good news that it's coherent, and it all works in one place. There's only one copy of the data. It's therefore always coherent. Backward application compatibility. So moving back to devices that may have wanted to open raw devices, block mode volumes. A block mode volume maintains the existing storage semantics. All operations traverse the entire storage stack. Okay, so if you have a filter driver in the storage stack, it gets to see all this stuff. It flows down the storage stack. Just in Windows, it uses an IRP, and it just moves along and turns into an IO operation at the bottom of the stack that copies it to the persistent memory drive. So we use this PM disk driver. Sector atomicity is guaranteed by that disk driver. And it's a shortened path length through the storage stack because we've modified a number of things to make it aware that there's PM at the bottom of the stack. There are no store port and mini ports down there at the bottom. There's no SCSI translation, or we don't have to take a user's write call and turn it into a SCSI write operation. We just simply copy it to the P map. So at the bottom of the stack, it is more efficient. You get better throughput with this type of device than you would with a traditional storage device. It's fully compatible with existing applications. It looks just like a disk. And you can create a file system on top of it, right? So, transparently you can create any old file system on top of this. The error semantics would be a little weird because they might not be aware that it was persistent memory device. They might have been thinking it was a traditional sector device down there. It looks like one to the file system, so that's how it will work perfectly. It'll work with all the existing file system filters. Block mode versus DAX mode is once again chosen at format. So this is just a picture of that I/O stack. You may have seen it before, but you can see in the left, there's a traditional thing with NTFS at the top, a volume snap layer, a volume manager, partition manager, the disk, the store port, the mini port, those are the hardware drivers, down to the SSD or HDD. Without that, with persistent memory, the middle line, we still have NTFS up there at the top and a vault snap driver with the volume manager. It flows directly to the PM disk. With a DAX volume, all that data flowing from NTFS down to the PM disk there's nothing in the middle there, right? It's flowing via loads and stores, mem copies. So there's no ability to throw in a vault snap at that point. Those writes go directly through in the hardware, in the processor. This slide might be a little bit of a redundant with what I said before, but it shows a couple of interesting pictures. It shows that both a block mode and a direct access application can share the APIs that flow through an SCM-aware file system down to SCM. All right? You get the true device performance, byte addressability for load and store. On the left, it's block mode. On the right, it's byte mode. Filter drivers may live in some parts of the stack. And for instance, Windows Defender will actually operate transparently on this thing. Windows Defender basically intercepts the create calls, not the read and write calls, right? So intercepting the create calls is simple because these applications still open that handle. So that's where they are hooked, if you will, to perform filter driver operation. But on the individual reads and writes, they flow through very differently on the right side of this diagram than from the left side. Performance. So this was Neil's slide from the IDF, from the Intel Developer Forum, but it shows some really interesting things. This was a rather simple benchmark run on current hardware. You can see the reference someplace else, but it's 4K random writes, pure write workload. One thread, okay, single threaded, no cheating here with deep parallelism. In fact, what we want to see is the latency. So we're running single threaded. We're running also on a single core, all right? And so we ran this speed benchmark with 3 different types of backing store. An NVMe solid state device. I should mention that NVMe is fully supported in all this too, right? Second, a block mode NVDIMM. That was the NVDIMM with that block mode driver on it, emulating the disk. And third, a DAX mode NVDIMM. Okay, that's one with a DAX file system and memory mapped access. Okay, so IOPS, 4K IOPS, single threaded 4K IOPS on an NVMe SSD with an average latency of 66,000 nanoseconds. And a block mode DIMM That came down by, the average came down to the latency rather, came down by a factor of 10. 10, pretty interesting. Megabytes per second, up by a factor of 10, right? Just walking the curve here on a single-threaded workload. DAX mode NVDIM, that same backing store as the block mode NVDIM, over 1 million IOPS, right? With 800 nanoseconds of latency for that, right? Megabytes per second, 4 gigabytes, a little over 4 gigabytes per second. So, that's free. Practically, how to use DAX in Windows. There are 2 ways to format it. The old-fashioned format command, /DAX is the keyword. And format-volume is the newer PowerShell mode. DAX volume identification. There's a quick API to see it. You get volume information, the API, and then it checks the return LP file system flags. There's basically a bit in the volume flags that says I'm DAX. You can also see it for a file. You basically get the volume information by file handle and check for that same flag. So the application can tell whether it's opened a DAX file or not. It chooses to. Memory mapping, this is basically how you might do it. At the top, the memory map, you create a file mapping. First you open a file. Each file is actually a file handle. You create a file mapping so you get a mapping handle. And then you use that mapping handle to map a view into your address space. And off you go, memcopy loads and stores. And then when you're done with your loads and stores and you want to commit the data, you call flush view of file. And so all these calls basically trap into DAX, create file mapping, map view of file, and flush view of file. All trap into DAX to do that magic work. But memcopy is purely a user space byte-oriented operation. Or you can use non-temporal instructions for better performance. And you basically create the same thing, but you do RTL copy memory non-temporal. And this uses the CPU intrinsics to provide the non-cached instructions, and poof, it winds up in your NVDIM. In the future, you could also use an open source NVM programming library. So these are just a few examples of ways to use a DAX file system in Windows today. So the final stage of this talk is just to wrap up a little motivation about a major application that happens to run on Windows, that happens to get a benefit from persistent memory, and that application would be SQL Server 2016. So this presentation, the full presentation is available online, but basically traditionally database transactions were gated by their log write speed. The log write was a synchronous operation that required very careful committing before you could retire the transaction, right? And so the latency of those operations gated the throughput of the database. The faster the log, the more updates were possible, the more transactions were possible in the database. So the goal was to use persistent memory to accelerate log commits, therefore accelerate the database and accelerate the SLAs provided to the customer. Log on SCM to place the log in storage class memory. Storage class memory is a handle that a lot of Windows products have used for persistent memory. We define storage class memory a little bit more carefully, but just think of it as persistent memory. We'll use the NVDIM support, and we'll expose the block interface. This uses the block interface at the moment, or the direct access interface. So if the app is enlightened, it can use DAX. And the example app we're going to use is going to be SQL. So this is what they did. Traditionally, on the left, in the past, log records were copied into a buffer, built up a block. Once the commit arrived, the log block would be closed, right? So this is a set of log records that are going to the persistent medium. The schedule I/O would persist it on a solid state device in general, because a solid state device is lower latency, higher IOPS. And we couldn't complete the transaction until that log commit occurs. So the model, Christian Diakonu, my colleague, gave a presentation on this at last year's NVM Summit right here. It's called tail of log. And instead of copying the log, it just copies the log records into a buffer in persistent memory. It builds the block persistently in pmem. And when the commit arrives, therefore it can be immediately completed, right? Because the log buffers have been placed in persistent memory. But the commit gives a signal that those log buffers are ready to go to some sort of persistent backing storage. And so it can actually lazily wait until this entire log buffer fills before committing it. So here, all 4 of those steps are colored in red. And they were, the completion, the latency of that was critically important to completing the transaction. Here, only those initial ones are in red. And you'll notice that only the first one has any overhead at all associated with it. It's basically just a mem copy. So, what were the results? SQL 16 can use, and it was configured here, to use a byte addressable log. It enabled on a DAX volume, and it accelerated in-memory database updates by about 2x. The net result, though, were shown here. So the row updates per second, about 2x, and the average transaction time went down a little less than 2x, just about. SQL does this today on Windows Server 2016. Darn it, keep hitting the wrong button. Okay, and last slide before I go, I have to mention SMB3. That's my baby. This is a slide that I presented at SDC 16. I just want to remind people that there are other things that can benefit from persistent memory, in particular, remote access, right? Which we typically do with advanced file system protocols, or possibly block protocols, but we prefer file system protocols for a number of reasons. Push mode is a model that I've proposed for SMB3, for RDMA actually, that SMB3 would deploy. And it requires an extension to the RDMA protocol to really take advantage. But it would actually, believe it or not, enable a zero-copy remote read-write. It would be zero copy on the client and zero copy on the server. And it would use the RDMA NIC to perform the copy. So I am very hopeful that this path, this purple path through push mode, will provide a zero copy in the future. But I am waiting for the RDMA commit extensions to become available. And we're working very hard on that in the SNIA NVM technical working group and with various RDMA vendors in the industry. Darn it, I did it again. And so more details available in these URLs. They're really long and complicated, I'm sorry. But follow them, especially these SQL Server ones, because I don't begin to give it justice in my little excerpt. But there's actually some video demos in here that will show you this stuff for real. And they all come complete with recipes for duplicating them yourself.
So, any questions? No questions?
It's the same question.
Ignore that, man.
Steve wants to know whether this is supported on ARM.
I can't give any product statement. I'm sorry.
Hi, Tom. I'm trying to understand why you have to do a copy at all on the cached I/O still. Because you're creating a user buffer, but eventually, even if you modify it, aren't you going to move it back to the original location? Maybe I misunderstood. I thought
The user buffer is the argument to the write file call.
right.
Right? He said write file handle buffer. Right? And that was a bunch of memory in his address space, in the user address space. Right? That was not on the volume. If he was doing that, he'd do memory map. He could do that with memory map. Then it's zero copy. Right? But the read-write API doesn't lend itself to that.
Okay, so it doesn't actually know where the real thing is on the MVDIM. It has to move it into the...
By design, it doesn't know where
Got
that
it.
is. It has a handle on which it's writing at an offset. Right, so it requires a copy. if he was PMEM aware or memory map aware, and he used the map view of file API, then he'd know the address and the offset, and he could do his own write using the CPU store instruction.
So the memory management unit couldn't take it out because it knows where?
No, because you'd have to take a fault. That's a common question. I'll repeat the question. Couldn't the memory management unit fake it out? The answer is, well, yes, but no, because you'd have to take a fault on every operation to know when to fake it out. And then you'd have to fix up the fault, perform the operation, and it would perform very, very, very poorly.
Yes, Tom, some questions on the performance. It sounds like you're using the same NV asset for the 3 different tests of...
No.
Oh.
No, the first one was an NVMe device, which was basically a PCIe attached solid state drive. The second 2 used the same asset.
And so the compression from DAX, from block to DAX, that was the same hardware, same offered load?
It was definitely the same offered load.
And
It was not, it was the same hardware, but a different software stack to get to it. Yes.
so most of the compression or the improvement in response time or reduction of latency was all coming from an improved or shorter software stack sitting on top of that hardware?
Yes, relative to the 2 second numbers. The first number was very different. It was preparing a block I/O and launching it down the I/O stack, sending it over the NVMe protocol to a PCIe device, getting an interrupt, blah, 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 lots of stuff.
Now, folks, don't block DAX.
The second one, the block mode NVDIM, it was creating a sector write, it was writing it down the I/O stack, it was copying it to a DIM at the bottom of the stack. The third one, it mapped the page of the DIM into user space and did a store instruction. It went through no software at all.
And were the contents changing, or were you sure that there was a copy getting written all the way down to the hardware? Right?
Absolutely, it was a write. We were performing the write in all 3 cases.
Some hardware gets smart, and when it's the same contents, they don't write it again.
No, this DIMs are not that smart. In fact, God bless them, they're not that smart, right?
Okay, thank you.
I'm going to win the award for the most pointless question of the day.
Oh.
On your slide, on your slide in your flowchart diagrams, you used a disk for a disk and used the disk image for NVRAM as well. My question, I guess, to SNIA is: are you going to standardize a new flowchart symbol for non-volatile memory?
You could pass that up to either to Mark or...
Yeah, would that be SSSI? What working group would that be?
It was
The disk icon working group.
Hi, Tom. The question I have is, SCM to recognize the NVDIMs and everything, what kind of hardware requirements we should have, like BIOS, and what kind of platforms are there that Windows Server 16 has been tested with PMEM?
Yeah, so that's a really good question and a really complicated answer. The DIM has to be a JEDEC DIM. There's a certain set of JEDEC tokens that are programmed into the DIM that are recognized by the BIOS and enumerated by Windows. Okay, and then the BIOS details are all called out in the Windows hardware compatibility criteria. They're all available through the regular Windows hardware channels. So you can read up on those extensively. I can try to get you some references. Sorry, I don't have them in this particular presentation.
One last question.
Hi Tom, I have a basic question. Does Windows also provide persistent memory to user applications with some interface?
Well, yes. In the 2 modes that I mentioned on the interfaces slide earlier in the deck. The first is DAX mode, where you open a file and memory map it, right? And that's direct access to persistent memory by the user's application. It requires a file system to be formatted a DAX file system to be formatted on the DIM. And the second is the NVM programming library, which is a user space API via various means on the platform, which may include DACs, which may include direct access to the device, but it becomes an NVML question. NVML is not yet shipping with Windows. There are some early versions available for Windows, and we have an intention to ship it as a component of Windows in the future.
Thank you very much, Tom.
Yes.